Hi everyone, welcome back. This is the second lecture of week 2. Now we'll be targeting the second objective of this week's lecture, which is defining endurance training. So in theoretically, endurance training is considered to be an intensity of 50 to 80% of your VO2 peak for 30 to 90 plus minutes per session, 5 to 7 days per week. So remember, prescription needs to be specific to the physical demands of the sport. So we see two pictures here of two different sports that are highly aerobic. One is tennis, which can last a long period of time and you need a solid aerobic base. And the other one is cycling. So you want to train specific to the demands placed on you. So for example, if tennis requires a higher percent of your VO2 peak, then you would train accordingly. So in theory, all activities of daily life in sports, team or individual sports, include endurance training. The question becomes how much formal endurance training is needed. So, for example, varsity athletes out there, many of you may be varsity athletes. How long is a practice? It's usually 2 to 3 hours. Is this representative of a competition? Is your competition 2 to 3 hours? Well, typically no. For example, swimming, you might have an event that lasts 30 seconds, but you're in the pool for 4 hours every day. So there's a disconnect here. You want to ensure that your training is specific to the demands of the sport and that you don't have this high volume of training without getting the intensity. So there's two questions I want you to ask. What activities or occupations/sports are considered endurance-based? And what are the practical benefits of having good aerobic base? Now, I want you to think about that for a minute. Write down activities that you consider to be endurance. Okay, conditioning is really not exclusive to endurance sports. An aerobic component is essential to all activities. And funny enough, conditioning is the most neglected from team-based sports, but has the highest transferability compared to strength training. So there is strength and conditioning coaches. Most people focus on the strength piece and in the gym, but they neglect the conditioning piece, which actually in the research has shown to be more transferable to enhance performance compared to strength gains in the gym. So for example, I remember in my hockey experience with Team Canada, we would do a lot of max aerobic power rides, where you sit on the bike and you sit for 40 minutes, and 20 minutes of that is almost at your max. It's very, very hard, really working to increase your lactate threshold. These I found to be fantastic. Like when I was on the ice afterwards, I found that because of those map rides, I was actually better and I recovered more. I could hit higher intensities. I was better at sprinting, et cetera, on the ice compared to any strength training I was doing in the gym. So it's all about transferability. All team sports have an aerobic component, have an endurance component. I remember doing a time motion analysis of myself when I played hockey. So I would wear a watch with a GPS and a heart rate monitor, and I had someone videotaping me. And for that entire game, afterwards, I downloaded my heart rate monitor and I correlated that to my playing time and showed that most of my time was spent with a heart rate less than 120 beats per minute. Very low level aerobic. When I'm recovering between shifts, when I'm gliding on the ice, there was only a small percentage of time that I was actually at high intensity of exercise. That just shows that team-based sports, although they're intermittent and considered anaerobic, there is a very large aerobic component. So anytime you improve cardiovascular fitness, this will directly benefit every activity, every occupation, and every sport. So ultimately, the aerobic system is the foundation. And the question becomes how much cardiovascular fitness is needed. And it really depends on the demands of the activity you're doing. As we can see here, even in a 100-meter race, you have 21% of the energy contribution is coming from aerobic metabolism, while 79% is coming from anaerobic energy contributions from ATP phosphocreatine as well as the ATP stores. So all of these events, you just change the proportion of each system. So the aerobic system is always being used. So it needs to be included in every program to improve or maintain depending on how much is needed. And this comes back to the needs and gap analysis, that you work with your client to determine what their needs are, what their gaps are compared to normative standards, and how much for that lifestyle and occupation or sport they need to develop their aerobic system. Now let's look at our third objective of this week's lectures, which is what are the limiting factors to endurance performance? The three main limiting factors to endurance performance is firstly delivery of oxygen to the periphery to the working muscle. The next one is the uptake of that oxygen at the contracting muscle. And lastly is the utilization of the oxygen for oxidative metabolism at the muscle. So delivery is the cardiovascular system. Uptake and utilization happen at the muscle level. We just talked about the limiting factors to endurance performance. And funny enough, the adaptations to endurance performance are the same, where we see an enhancement of the delivery of oxygen, the uptake of oxygen at the muscle, the contracting muscle, and the utilization of that oxygen at the contracting skeletal muscle. So we had what the limiting factors also are the adaptations that take place in those three specific areas. So now let's talk about the delivery piece. The cardiovascular system, the heart and the vascular system, all our vessels, so our arteries, our arterioles, our capillaries, our venules, and our veins, help in delivering oxygen to the working muscle, but also bringing that back to the heart. So when we do cardiovascular training, this system becomes more efficient. And as such, we can have in every contraction of the heart, we have more blood, more oxygen being delivered for a lower heart rate response. So essentially, there are three main things that happen. And you can see this in the chart here. It provides an overview of what before training and after training, and then elite athletes. And I want you to be aware of what is changing, not necessarily memorizing the numbers, but you have to be aware of what's happening to resting heart rate. What about maximal heart rate, etc. So ultimately, there's three main ways to enhance delivery of oxygen in our body, in our system. One is a stronger heart, that our heart is a muscle that when you train it, it gets stronger. So because it gets stronger, we can actually, when it contracts, we can eject more blood per contraction. So this is an increase in stroke volume. And this is due to that stronger heart, increased size, and increased contractility. The second main way to enhance delivery is something called angiogenesis. Genesis being the creation of, and angio is new capillaries. So it's the creation of new capillaries, the creation of new vessels, which help in delivering more oxygen to the working muscle. There's a greater surface area to provide oxygen to the working muscle. And thirdly, the third way to enhance delivery is by increased oxygen carrying capacity, by increasing red blood cell mass and hemoglobin mass, which we'll talk about on the next slide. Those are the three things: stronger heart, angiogenesis, and increased oxygen carrying capacity by increasing red blood cells and hemoglobin content in the blood. So now let's talk about the delivery of oxygen. Well, oxygen needs a taxi in the blood, like many things. It can't just freely move around the body by itself. It needs to be bound to a protein. And in this case, that protein is called hemoglobin. So hemoglobin is found in red blood cells. So in the optic on the left side, we see the oxygen from the lungs, as indicated by blue dots, being dissolved into the red blood cell, binding into the hemoglobin of the red blood cell. Now we have oxygen in the red blood cell. This then goes to the target tissue. In this case, we see the stomach and the liver, where oxygen is offloaded to that tissue, taken up by that tissue in the form of myoglobin, and then that tissue can then use the oxygen for oxidative metabolism. So oxygen cannot travel around the body by itself. It needs to be bound to a taxi. It needs a taxi to take it. And in this case, we have hemoglobin that delivers the oxygen in the blood, and myoglobin that takes up that oxygen at the skeletal muscle to be able to transport it to the electron transport chain where it's needed. So one way, unfortunately, some endurance athletes try to cheat the system is by doping with something called EPO, erythropoietin. And this stimulates the bone marrow to increase the amount of red blood cells you have in your body. So if you have more red blood cells, that means you have more taxis available to deliver oxygen. So if you have more ability to deliver oxygen, you can increase the body's ability to produce energy through oxidative metabolism, and endurance performance will be improved. So Lance Armstrong, notorious for this, 7-time Tour de France winner, was caught multiple times with EPO doping. So he cheated by artificially taking in EPO to try to stimulate the bone marrow to increase red blood cell production so that he could deliver more oxygen to the muscle. And it worked. He was the best in the world for a long time because he doped. So why is EPO banned in endurance sports? Well, one, it provides an unfair advantage, but two, it is not safe for the user. So, for example, Lance Armstrong, by supplementing with EPO, he increased the amount of red blood cells in his body, which means his blood is more thick, and your heart has to work harder to pump that. And over time, it can lead to a heart attack, that you have more viscous blood, which puts more strain on your heart. So things are banned for a reason. One, it provides a competitive advantage, which isn't fair. And two, it has health implications for the user that can be negative.